I owe my research career to Spider-Man. When I was doing my postdoc at MIT, I noticed a journal article on a colleague's desk with this as one of the figures. And in that paper, the authors had mimicked gecko adhesion to create a dry adhesive tape. And since that time, I've committed a huge part of my research career to bioinspiration, where I look at nature for new ideas to solve medical problems. Now, what I've realized through the last decade or so of research is that you can't simply mimic nature to solve problems. In fact, I've discovered that there are 4 rules that one must follow to successfully steal from nature, and today I'm going to share them with you and provide examples of how they apply in the lab. So rule number 1 is that you can start from the problem or the solution. So here's an example where we started from the problem. Babies that are born prematurely suffer all kinds of injuries when tapes are removed from their fragile skin. And these tapes are used to affix monitoring devices. And they have 2 layers, a backing that you see and a glue that attaches to the skin. Now, for you or me, when you remove these tapes, it either breaks at the interface of the glue and the skin, so it just comes off, or it breaks within the glue, which is sometimes when you have a Band-Aid and you remove it, you have glue that remains on your skin. So we turn to spider webs for inspiration. Spider webs have non-sticky regions the spider can walk on, and sticky regions that can capture prey. So we created a 3-layer adhesive that has a backing, a new middle layer, and a glue that attaches to the skin. And for that middle layer, we etched a grid pattern in a silicone material with a precise chemical properties and thickness that after it performed its function, we could simply peel from a corner and remove that backing entirely from the adhesive, leaving 100% of that adhesive behind. And that's not a problem because the adhesive is extremely weak, so you can just simply remove the tubes or other devices which the tape is using to affix those monitoring devices. Here you can see how the traditional medical tape tears the skin, ouch, but whereas the new tape leaves the fragile origami paper intact, or in the case of the neonates, their fragile skin. You can also start from the solution first. We noticed that spiny-headed worms latch onto their hosts by blowing up their noses following insertion. Where might that apply? Swellable microneedles for better skin grafts. So typically, staples are put at the periphery of the graft, and the middle part doesn't always adhere. So we engineered microneedles whose tips swell following insertion into tissue. So this could maximize adhesion and maximize surface area of contact to prevent a painful regrafting procedure. Rule number 2, precisely define the problem. Successful problem definition must precede successful problem solution. Meet Jim. Jim has prostate cancer that has metastasized throughout his body. And following the removal of his primary tumor, his clinicians are desperate to identify new drugs that can kill the residual cancer. A promising approach involves taking a sample of blood from the patient and passing it through a device to isolate the circulating tumor cells that are released from the metastatic sites. However, there are 2 problems with this approach. Most of the devices involve capture of cells on a surface, so cells that are streaming by a human hair away will not be captured. And for those cells that are captured, it's nearly impossible to remove them. They're just so tightly bound. So we asked, what creature in nature can capture things at a distance? Bingo, jellyfish. Jellyfish have these long tentacles that extend far from the main body to capture food and prey. So we developed synthetic tentacles made out of DNA that have repeat units that could strongly attach to the surface of cancer cells. And we can immobilize those synthetic tentacles on our device. Here you see a microparticle in solution. We're holding it there. And we've actually decorated it with these synthetic tentacles. Now, you can't see them, but in a moment, you'll see their impact. We bring a cancer cell in close proximity, but we don't let it touch. The tentacles have engaged, and watch what happens when we retract that cell. We're able to pull that particle out of its original position. Here you can see the DNA tentacles on our device in green wrapped around a cancer cell in blue. Our device was able to achieve the same high efficiency of capture as the best devices described. However, we were able to do it at 10 times the flow rate, meaning we could flow 10 times more blood through our device in the same amount of time. And because this is made out of DNA, we could easily just add enzymes to release the cells in pristine, viable condition so that we could study them and determine which drug could kill the residual tumor. Rule number 3, surround yourself by many examples in nature. This can involve spending time in nature or searching the web for examples in nature. Someone from my lab actually visited the zoo for inspiration. A zoo is a living library of possible answers. And our colleague observed porcupines, and we became very fascinated with their quills. Now, anyone who researches porcupines will quickly find the graphical definition of pain. Now, I'm a scientist, and there's a subset of us that like to do self-experimentation. So I just had to put these quills into my chin to get a sense for what this feels like. And I gotta tell you that despite the look on my face, I was quite surprised how minimal pain there was on insertion of these quills and the minimal force that was required to actually push these quills into my chin. There we are again, learning from nature. These quills have tiny microscopic barbs that decorate the tips that have incredible interaction with tissue. And it's amazing because these barbs are so small. They're the size of a human hair. Look how much pull-out force is required to remove these quills from tissue. We see barbed quills on the left, and on the right, barbless quills. We've just gently sanded those barbs away. Look at that. Pull-out force is important to seal wounds and keep them shut. But here's what really caught our attention. Look how much tissue damage is caused by insertion of traditional surgical staples into tissue. The hole that's created is always larger than the staple itself, and bacteria can get in. And you need to bend them. Quills can avoid all of these challenges. They go into tissue with minimal damage, and the barbs actually act like the serrated features on a serrated knife, slicing through a tomato. You can make staples with quills on either end that easily insert into tissue, making perfect holes, so no risk for bacterial infection, and you wouldn't need to bend them, so less tissue damage on the way in and less complicated devices to place them. You could also make the whole system biodegradable, so it would just degrade over time, and you wouldn't need to remove it. Rule number 4, successfully stealing from nature requires the right people and the right tools. And we are all gathered here at TEDMed to harness the power of a multidisciplinary community. And in my lab, we try to harness that power every day. This is the heart of a baby with a septal defect, a hole in between the chambers of the heart. Clinicians are desperate to identify new adhesives that can seal these holes, and they have to work in the harshest environment in the body, inside a beating heart. And they need to remain in place and not be fouled by the presence of blood. So we looked into nature at creatures on the land and in the sea that exist within wet, dynamic environments. Slugs, snails, sandcastle worms. They all had these viscous secretions that stay put, like honey on a plate. And they contain hydrophobic agents that repel water. So we said, why don't we develop an adhesive like that was hydrophobic and remained in place because it was viscous? And then we said, well, why don't we also make it biodegradable and biocompatible so it would fully degrade over time and then be replaced by the patient's own tissue? And then we said, well, why don't we also make it light activatable so the clinician could cure it when they're ready? To address all of these challenges, we required a multidisciplinary team with access to state-of-the-art tools and technologies. We had multiple clinicians, biomaterials experts, device experts, and we also had someone to help us deliver light inside the body. Now, if anyone here is squeamish at the sight of blood, now is a good time to grab onto the person beside you. Here we make a 2-millimeter defect in a rat heart, and we close it temporarily with a suture. We've actually developed another material, a patch, which is fully degradable and elastic, also transparent. And we coat the glue on the underside of that patch. And you'll see we don't really remove too much of the blood during this procedure. We then apply the patch, the glue is facing the tissue, and we shine light for 5 seconds. But something went horribly wrong. The patch actually slipped away from us, completely unexpected. We didn't know what to do. We had to act fast. So we removed the suture, and we scrounged up as much glue as we could find. We put it onto a spatula, and then we applied it to the leak. And it did exactly what it was supposed to. It repelled the blood because it was hydrophobic. It remained in place because it's viscous. Enough time for us to shine the light. Following another 5 seconds, we end up with a perfect seal. We took these animals out 6 months, and they did fine. From this experience, I realized that there was actually a 5th rule, that bioinspiration requires adaptation. I am not showing you the tons of iterations that each of these technologies had to go through. Simply mimicking nature was not enough. It required patience, humility, and often lots of ideas from lots of people before we could get to the right answer. So there you have it, 5 rules. You can start from the problem or the solution, precisely define the problem, look at lots of examples in nature, get the right people and the right tools, and let your solution evolve. So it all comes back to Spider-Man. That's the ultimate example of stealing from nature. And I recall an important message that Spidey's alter ego, Peter Parker, learned from his beloved Uncle Ben, who said, "Peter, you must never forget that with great power comes great responsibility." I believe that we are all empowered by our ease of access to state-of-the-art tools and technologies, by our ability to look at nature and leverage its secrets. But it's up to us to learn the rules and to maximize our impact in a responsible way and do all that we can to make the world a better place. Thank you.